Thank you very much, Alice. Good evening, everyone, and welcome to this first Open University event in partnership with the International Festival, Milton Keynes. My name's Dr. Julia Cooke, and I'm the Associate Dean for External Engagement and Enterprise in the STEM faculty. I hope you enjoyed seeing Luke Jerram's 7-metre diameter Mars sculpture as you came in, because it sets the scene so beautifully for tonight. This evening, we're going to be unlocking the secrets of space with talks from 4 Open University academics. Once they've all spoken, we'll welcome your questions for them about their research and any general space questions. The Open University has a long history of world-leading space research in planetary science, astrobiology, astronomy and space exploration, which contributes to major international space missions. Our researchers are involved in the development of scientific instruments for spacecraft, the study of extraterrestrial materials, including meteorites and lunar samples, and the analysis of data from missions such as the European Space Agency's Rosetta and ExoMars missions, and NASA's Curiosity and Perseverance rovers. Astrobiology OU is leading the way in planetary protection, space governance, and astrobiology ethics. The university has an excellent track record in the translation of space research into activity here on Earth and terrestrial applications, and is driving new initiatives in Earth and environmental sciences. But tonight we're looking forwards and outwards, and we're going to hear about cutting-edge research that's happening right now. So it's my pleasure to introduce Professor Mahesh Anand. His research focuses on the formation and evolution of planetary bodies in the solar system through analysis of samples from the Earth, Moon and Mars. Recently, he became one of the first international researchers to receive lunar rock and dust samples from China's Chang'e 5 mission. Mahesh, over to you.
Thank you very much, Julia. Good evening, guests, citizens, explorers. Yeah? It's my great joy and honor to welcome you to the Open University. On behalf of our team that has put together this fantastic event over the next 3 days, I would like to welcome you to explore what we have here on offer, and do return, because we do these type of events quite regularly. And the next one after this one will be in December, that we call the Moon Night. So without further ado, let me go into my slide. Do I move the slide or? Oh, there we are. So I have only one slide to talk you through, and it is simply to share with you the reason why I'm standing here. So I am representing the Open University. And at the Open University, we believe in our mission statement by action. And what I mean by that is we believe in the idea of people, places, methods, and ideas. And I will just walk you through some of those things and how that actually translates into our daily work here, particularly using Moon as an example. And you'll hear from my colleagues about other planets and other research that actually they are undertaking. The idea here is not to give you and tell you everything that I do, but just to give you a flavor of what is out there and why you may be interested, and why particularly those of you who potentially could be walking on the moon in the next decade or 2, yes, should be actually getting engaged now. So I primarily work on the moon, on lunar exploration. I was one of the scientists involved in discovering water in lunar rocks. And that has been a game changer. Why? Because to explore space, you need water as a resource. And water is one of the most expensive commodity in space. So if you can actually produce your water and use it when you are there, you not only reduce your cost, you also reduce the risk of getting stranded without water. And in a way, that has really catalyzed all around the world. It's almost like a new space race where every space agency, even commercial companies, now want to go to the moon for prospecting and actually extracting resources, starting with water. And the next big thing from water you can derive is something that we take it for granted every single day. And that's the oxygen that we breathe. because you can actually split and electrolyze that water to extract the oxygen that can then be used either for astronauts to breathe, or you can use that oxygen to use it as a rocket propellant in distant future. Not tomorrow, but in distant future. You get the idea. And the other thing that actually Moon gives you is it gives you an easy access to space. Moon is the nearest planetary neighbor to the Earth. 8 people have already walked on the Moon, believe it or not, right? And when they visited the Moon, they actually collected a lot of scientific data. They carried out a lot of research, and they brought a lot of lunar samples back to the Earth. And I work on those samples. So I'm actually a beneficiary. 50 years on, I'm standing here being the beneficiary of those pioneers who actually put their life at risk, went all the way to the Moon to conduct scientific research and bring those precious samples back. We are still analyzing those samples here. We have PhD students sitting here in the audience who are actually developing their careers based on the analysis of those samples. And as you heard from Julia, I was in China 2 months ago receiving the first Chang'e 5 samples that has ever been given to anybody outside China. And we have it here in Milton Keynes. And I want you to celebrate the fact that in Milton Keynes, actually, we are leading world research in this context. Now, we are not stopping there, because on the right-hand side, you see 2 other pictures, one of which is BBC getting quite excited about our research, where they actually said, oh, these people are extracting water from the lunar dust. We are not only extracting water, that's the beginning. What we want to extract further are different metals and different elements that could then later on be used for constructing various tools, various bits of pieces that you need, whether it's a wrench or whatever else it is, from the local resources that are there on the Moon. And that's why I conceived the idea of what we call living on the Moon. So it's not about going to the Moon once. It's not just about going to the Moon and doing something and coming back. It's actually going there in a sustainable manner, in a responsible manner, and making use of the resources. So almost we are going 5,000, 10,000 years back to our ancestors when they only had rocks and the soil to then make do with it. So Moon presents us with that challenging environment, but in this day and age where we've got 8 billion people in the world, we have to make use of the resources, limited resources that we have in a sustainable manner. And I think that a target body such as the Moon, and one day even Mars, would actually provide us with that opportunity. So right now we are using Moon not just for exploring the solar system, but also learn to live within constrained environments. And finally, I want many of you or most of you to be moonshiners. Right? Who doesn't want to actually enjoy the Moon? You don't have to go to the Moon. A week ago, the Moon was bright in the sky. It was rising. Right? Every other day, if you actually are lucky and the sky is clear, you can get a glimpse of the Moon. That is the bright, shining object in the sky that we all relate to. And we can use it as a stepping stone to go and explore the rest of the solar system. I think with that, I will hand over to the chair. Thank you very much.
Thank you, Mahesh. Our next speaker is Julia Semprich, and she's a petrologist and planetary scientist who's studying the crust and mantle of rocky planets and understanding what that means for their habitability. Tonight, she's going to speak to us about Venus's crust.
Thank you very much, Julia. Yes, so I'm here to talk to you about the hottest planet in the solar system, although we're getting there with the summer. And that is Venus. Venus is often called Earth's twin because they are very similar in size and they have a very similar density, but that is where the similarities end. Because, as we know, Earth has a mild climate, has surface water that makes us able to live here, whereas the surface of Venus is really hot. It's 470 degrees Celsius, so if you actually could survive, you could bake a pizza on the surface. But it also has a very CO2-rich atmosphere. And this is what you can see here in this picture. So these are actually the two ways we can look at Venus: the CO2-rich atmosphere, the extreme thick clouds, or otherwise we can look a little bit through the clouds and with radar methods and then we can see some features on the surface. This is a false color image. It's often shown as the one Venus image. This is not the real surface. This is just false colors, and everything that looks bright is actually just rougher surface. So it doesn't necessarily mean it's a specific feature on the surface. And because of these conditions, extremely hot, these really thick atmosphere, missions to Venus are very difficult. And there's so many questions we still haven't answered about Venus. It's a very puzzling planet. So trying to figure out something about the evolution of Venus is very important to us because we want to know what makes a planet diverge differently from Earth. And that is also important to study the increasing amount of exoplanets that we find. Many of them are actually looking a lot like Venus. And I'm mostly interested in the crust. And the little we know about the crust comes a lot from some missions that actually did land on the surface. So the Soviet Union managed to land 2 missions on the surface. One was Venera 13, well, actually several missions on the surface, sorry. And the 2 I want to present here are Venera 13 and Venera 14. And these actually got images from the surface of Venus. So this is how the surface of Venus looks like. And they also, which is important for me, brought back some whole rock compositions. So they measured the composition of these rocks. And with these compositions, we can do some modeling and try to understand what actually happens in the crust. And this is a short summary of one of the recent research we did. You don't have to understand everything, this is a sketch. And I will explain a little bit what we are actually doing. So you see the scale here, that is a kilometer, that's the depth going into the crust and the mantle. And then I have this annotated here. On top, we see different heat flows, different thermal gradients. So the heat flow is actually the heat that comes from the interior. And for Venus, we don't know this, but for a planet, usually it varies a lot. So on Earth, examples here would be Iceland. So if you go to Iceland, you have a lot of thermal energy coming out. You have the hot springs. You actually can see that the magma is really close to the surface. Sometimes you actually are lucky and find an eruption. But that is really high heat flow. Whereas here in the UK, volcanism has been a while, so it's actually relatively low heat flow. For Venus, we don't know exactly how high it is, so this is why we vary it. Then we have a compositional variation. You don't need to know these names. It's just different variations in chemical elements that we try to figure out what could be there. And then we try to calculate the thickness of the crust. And so the crust here is shown in the blue and the red. The red just means it's a slightly different mineral assemblage. And in green, I show the mantle here. And so there's 2 different things that define the thickness of the crust. One is at low heat flow, it's a densification. And that means that we have, the crust actually can get denser than the mantle and can potentially sink into it. You know this, probably this isostasy principle, if you look at a piece of wood on the water, that will flow, whereas if you put a rock into the water, it will sink down. And it's the same principle. The other limit is melting. And the hotter it gets, at lower depths, it will melt, and that will define the crustal thickness. So I have a little bit more, if somebody's interested. This is the paper that actually describes all of this. And with that, I would like to thank you. If you would like to follow me, I'm on Mastodon. So thank you.
Thank you, Julia. That was perfectly timed. The third speaker you're going to hear from tonight is Dr. Peter Fawdon. He did his PhD here at the Open University and is a planetary geologist who uses remote sensing and mapping techniques to explore planetary surfaces. He uses the records left behind by volcanoes, rivers, and impact craters to investigate the history of Mars. And this evening, he's going to talk about how he uses imagery to do this. Welcome, Peter.
Okay, thank you very much. So I'm here to represent the sort of planetary exploration from the sort of imagery and geomorphological approach. So fundamentally, looking at pictures of planets and working out what's going on them. That's what I do, what I bring to planetary science. And there's quite a lot of that here at the Open University in the Planetary Environments group, studying Mars, Mercury, and anything else that you can get a photograph of in the solar system, really. So, as I said, fundamentally, this is my work is about remote sensing. It's looking at the surface and then from that understanding what processes have occurred on that surface. So in this example here, I've got a little sort of schematic connecting Mars on one side, an image from 2019, global weather imaging actually, connecting to the Cassis camera on board Trace Gas Orbiter, a satellite that there's a model of just outside there, and one of the images we get back from that mission. So in this image, where the different colours are telling us about the different minerals that are made up across the landscape, and the different textures in the image. You can see a sort of a hill thing in the middle at the top, and sort of like a ridge lump down the middle. They're very basic observations. Tells us about the sort of the shape of the landscape, so sort of what it's made up of and what it looks like, sort of like how it feels and what it tastes like, kind of, if you want to be like that. And then we can use this to make interpretations about what's happening in the landscape. So in this example here, lots of geological knowledge will go into being able to tell us that this is a landscape with something where there was a river once upon a time that has subsequently been buried. The rocks around it have reacted with water in the ground, and then it's some form of erosion has removed some of the landscape to allow us to see this, what once was a river, now is a ridge. But like, how do you get that knowledge? Like, how do you go from this blue and orange image to that? Well, basically, we're using our understanding of Earth and applying that to Mars. So what we see on Earth and our understanding of those processes can then inform us about what is happening on Earth. So in this example, this is exactly the same process as I just described, that what's called inversion of terrain. And in this example, this is a river. Well, once upon a time, where we see a ridge in that image, that would have been a river in the Jurassic period, and now it looks very much like Mars. We can use this study here to understand something similar on Mars. But that is just one process in one place. And the tool we use to explain all of the things that are going on, because not just one thing happens on Earth or on Mars, in fact, many different processes happen over time, and they all end up on top of each other, making a big sort of pile of rocks. And to try and understand that, we use geological maps. So the map is, as I've written here, so it's a visual hypothesis of summarising all of those basic observations. There's a wobbly, lumpy bit, there's some pink, well, some blue bits, and there's some white bits, and puts them together and allows us to sort of formulate a sort of bunch of hypotheses about what we think might have happened, so which is sort of a geological history. So in this instance, perhaps there was the edge of a big lake and when the water level went up and down for whatever reasons. So that's the tools we use. So now I'm going to take you into why we're doing this, why this map in particular was created, and why the sort of Cassis camera and the ExoMars mission is sort of happening. So the purpose of this particular map is to connect the orbital understanding of how the landscape on a really big scale works through to what the ExoMars rover, the European rover that hasn't quite gone yet, but it will do, and bring those things together. So this sort of shows you, this sort of fly-through puts those things together. So you can see the map, and these different coloured areas represent different geological units, different types of rock formed in different ways. And you can see how they're all across the landscape. And sending a rover to investigate different ones of these will tell us different things about the ancient environment when those rocks were formed. You can see here the Cassis data and how the variety of colours is interpreted in the map. And as we sort of come in close, you can see how we will, when the rover gets there, we'll be using the map to help decide where it should go for it to try and fulfill its sort of fundamental goals of the mission. So this is the actual scale of the rover in the scale of the whole of that fly into Mars. It's about 2 meters high. So that brings me on to what the work we're doing now that this mapping and this understanding from orbit is complete. So what we do a lot of here at the Open University, in fact, a huge amount of the UK planetary science community is involved in, is the ExoMars rover. So this is the Amalia, not the actual rover. This is what's known as the ground test model. And this is in a really boring warehouse in Turin, in Italy. And this is the model of the rover, which all the commands which will be sent to Mars to command Rosalind Franklin, the real rover, are tested on before they go, to make sure that the sequences of commands aren't going to break anything, basically. And this is a video I took last year when we were doing some simulations of those operations. And so what we do at the moment, and most of the UK is working on the eyes of the rover up here. This is the PanCam instrument, and just underneath that little gold bit, the ENFIS instrument, which means rainbow in Welsh. And they are between them, they're the eyes of the rover. They see what's going on, and then the ENFIS does the minerals. And that is the purpose of that camera is to identify where the rover should go so that the ExoMars rover can complete its sort of primary mission, which is to use the drill, as you can see, this sort of black box on the front here, to drill up to 2 meters into the Martian subsurface, where it has specific instruments inside which will be able to identify sort of physical and chemical evidence for life in a fingerprint that you can't kind of mistake when it goes there. Okay, thank you very much.
Thank you very much, Peter. And last but not least, we have Dr. Nisha Ramkissoon. She also did her PhD here, and she's also a planetary scientist who's working in the interdisciplinary field of astrobiology. Nisha tonight is talking about icy worlds research that's carried out here at the Open University. Nisha.
Hi, yeah, so my research very much focuses on how geological processes can influence the evolution and habitability of different planetary bodies, and this includes the icy moons, and that's what I'm going to talk to you a bit about today. But first of all, what are icy moons? And when I'm discussing icy moons, what I'm really talking about are these moons that orbit around the giant outer solar system planets, like Saturn, Jupiter, Uranus, and Neptune. And some of their moons are actually covered with ice. Now, this is predominantly water ice, but you can also find some different types of ices out there because it's so cold, such as ammonia, and we can also find some non-icy material, such as rocky material, as well as salts. Now, on the slide here, you can see a few selections of icy moons that have been discovered, and 2 of them you may be more familiar with, which is Enceladus and Europa. Now, these particular moons you may be familiar with because you've probably heard about them a bit more in the news because they get a little bit more attention. Evidence has suggested that these particular moons may have subsurface oceans that exist underneath that icy crust. And of course, with the presence of liquid water comes the possibility that life may exist there. But to really be able to assess whether or not life can exist on these different icy moons, we need to have a better understanding of what the subsurface oceans look like, especially in terms of composition, to determine whether or not life that we're interested in, which is particularly microbes, would be able to have enough energy and enough material to support their growth and metabolisms. But of course, this is very difficult to do because the surfaces, as the name suggests, are covered in ice. And these ice crusts can be like kilometers to tens of kilometers thick, which makes it very difficult to get any analysis done. But we do have some information that we've gathered from the surface of these moons that we can begin to use to help us constrain the underlying environment. And this is the kind of research that we've been doing here at the Open University. So some of the research looks at these subsurface ocean environments. And what we know based on the surface expression of these icy moons is that they have these salts, and these salts are most likely formed as a result of the ocean interacting with a rocky layer. So we can use computer modelling as well as laboratory experiments using high-pressure reaction vessels, such as in the image, to simulate these different types of water-rock interactions between different types of candidate rocky materials. And that can help us constrain the different types of ocean chemistries that may exist on these icy moons. Another part of research that's conducted here also examines processes that occur in the icy crust. in particular freezing, which can influence the non-icy material that I've mentioned before, which would be salts, and how we observe them on the surface. So using lab experiments and lab equipment such as the cryo stage, which is connected to a Raman spectrometer, which is in the bottom corner over there, we can take potential analog samples of ocean chemistry and freeze them and see what kind of salts would form. We can do this in the lab. Research is also done using samples collected from the field, and this kind of helps us understand how the salts on the surface of the icy moons connect or can actually represent the ocean underneath and provide us with a bit more information. But of course, the icy crust is also exposed to space, so that also means it could be bombarded by impacts as well as solar radiation. So we also look at how these salts can be modified by these different processes. And of course, we also look at whether or not life can exist in these different in these oceans. So we can look at, based on the ocean chemistries that we've modelled and produced through experimentation, we can try and assess how much energy can be available through that, through further modelling, as well as taking microbial communities from like the natural environment and analogue sites and putting them into our simulated environments in our reactors and seeing whether or not they grow. We also look, and if they do grow, we also look and see how these microbes can be preserved in like different materials, in particular like salts, so they can be detected by future missions that go to these worlds. Another aspect of the research that gets conducted here looks at whether or not if life from Earth can be transferred on these spacecrafts and then contaminate these different worlds, which obviously wouldn't be great, especially if there is native life that exists on these planets. So that was a really like whistle-stop tour of the types of research that we do here in the Open University relating to icy moons, but hopefully you got that we take a broad approach to looking at and understanding what's going on in these icy worlds. And all of the research done isn't just done by me, it's done by a team of people, including researchers and some great technical staff who help us, who facilitate us and make bespoke equipment so we can actually do do our research and simulate these different planetary environments. Thank you.
Thank you very much, Nisha. So that's all 4 of our speakers, but we now have plenty of time for questions from you because we're interested to hear what you want to know more about and what your burning questions are. We're just going to bring an extra chair on so we can sit together. We have Moni and Mark with some roving mics. So if you've got a question, please put your hand up and a microphone will come to you. And I'm going to switch slides and shift over to join them. So I can see some questions right down the front. Maybe we could start there. Oh, I need to bring a microphone. Oh, I've got one microphone.
Hello, great introduction to your work, everybody. I was wondering, we've seen water jets coming from moons. We've seen water jets coming from stars, young stars. We've seen water jets coming from sunspots at times. We've seen water jets coming from comets. We've seen water jets coming from black holes. We've seen water jets coming from the Earth. Are any of you interested in a unified mechanism behind all of this?
I can say something.
Yeah.
Oh, I am.
Yeah, you are.
I'm alive. Seeing lots of different phenomena that look very similar in very different contexts is one of the kind of big challenges in planetary science, really. I can't comment on water jets in such diverse environments, not being an astrochemist or astronomer, but I can say that there's the challenge of like what's known as convergence of form, where many different processes can create landforms that look essentially the same, is a big problem. If you've got a lumpy hill, many different things could have formed that. And so it's really important to look at the context that those phenomena or landforms occur in. That lumpy hill might look the same if you looked at it closely, but if it was on the side of a volcano, it's probably a volcano related. If it's in a big ice field, it's maybe something that's known as a pingo. They look very, very similar, but fundamentally very, very different processes. So That's all I would say there. Yeah.
Did you want to add anything, Nisha?
No, I was just going to sort of say this, a similar thing. Like, the reality is like on Earth, it's sort of like one data point, and it's only affected by the conditions on Earth, and that's the only things that we know about. On different planets and different bodies in the solar system, we've got different conditions that occur, so they may come up as a result of different processes.
Thank you. I can see another question here. I have to make sure I might move my chair a
I've
little
got
bit.
a bit of a stupid question. I'm not scientific at all.
No such thing.
Don't know
Ask away.
anything about astronomy, but there's something puzzling me. Is all water the same? Are you talking about the water there being what we would recognise as water, or is it a different format, or is it a different kind of water? Is it all the same? Is it all different? Thank you.
I can see you nodding, Mahesh. Would you like to take that question?
Right. Yeah. Great question. I mean, this is a thing that shorthand everybody says water, but everybody means different. They don't mean H2O, liquid water that we are so familiar with. So oftentimes it's a shorthand. Whether you detect hydrogen, you assume that actually it is combined with oxygen, and if it is combined with oxygen, then it is either hydroxyl or molecular water or a component in between, right? So you're right that not everybody's water is the same water, and then depending upon the environmental condition in which those, hydrogen and oxygen atoms are next to each other, they can be present in various forms, so the gaseous form or the ice form or the liquid form. So it again varies, but the short answer is no, not all water is the same. But the assumption is that if common law of physics applies everywhere, and if you do have a hydrogen next to oxygen under the right circumstances, you can produce the water that we are all familiar with.
That was a great question. I can see people pointing up here. There's someone in an orange shirt. I think we've only got one microphone, so that microphone's going to have to be busy. I'll just sneak through. Great, ask away.
Why are we looking for life on Venus if it's the hottest planet?
That sounds like one for you, Julia.
Maybe, yes. So it is currently the hottest planet, but that doesn't mean that it has been for all its time. So there are indicators that it might actually have had even oceans early on, and then it lost all of these oceans and became as hot as it is. It is very difficult because our data sets are so limited, but if it actually had water early on, it could have been a very habitable environment, and it could have started out very similar to Earth.
Okay. Just,
Yes, go.
Another thing to add is that not all of Venus is all that hot and difficult, because you people probably are also remembering the recent news story about the phosphine detection as potentially a marker of life form. So again, one should not close our minds to the possibility that actually under certain conditions where very high up in the Venusian atmosphere, perhaps you have conditions which are a bit more favorable to having not necessarily the kind of life that we all know of, but some form of biomolecules. I mean, that's what is also exciting scientists. I'm not saying that they have found it, but all I'm saying is that this is the reason why people keep searching at places where you first don't expect, but if you don't look at those places, you never find something. So I think the whole point of doing scientific research is to be driven by curiosity and then put together the evidence that you then gather together to make a logical conclusion, whatever seems correct at that time.
Thank you. Where's our next question? We've got a couple down here, so we'll take the man in the check shirt first, and then the man behind them.
I'm interested in the moon rock samples that you've been working on. You've discovered water, I presume it's not just molecular water. What form does that take, and how do you sort of go about analysing for it?
Fantastic. Thank you very much. That's a great question. So again, as I mentioned before, not all water is in molecular form. So in this case, the water that I'm talking about is at most is hydroxyl. So it's an oxygen atom attached to a hydrogen, and that hydroxyl is actually sitting inside a mineral called apatite. Now, apatite is a calcium phosphate mineral that is known to contain in its structure hydroxyl molecules. Right? So that's what we detected. Now, if you happen to go on the lab tour, I'm not sure if you went on a lab tour. If you didn't, those of you who went on a lab tour, you might have visited a lab that we use called NanoSims. Moni might have given you the tour. But that particular instrument is what at least my team used here at the Open University to detect the presence of hydroxyl in the lunar rocks. And we did not only detect the presence, we also established its nature. In other words, we did its DNA fingerprinting in geology equivalence. And we found out where that water or the source of hydrogen might have come from. So I think we are not only interested in knowing how much of that hydrogen is attached to oxygen, but where that original water could have come from. That is a big question.
Thank you. And there was a question just behind that same person.
Oh yeah, it's working. What are you hoping to be the results coming out of the Europa Clipper and like the data and things that comes out of it? What is like your optimal outcome? And I've got kind of a follow-on question for that. Like, I think for like decades we've known like there may be a sea under Europa and a desire to explore it. Is there a feeling like from the public about how quickly space exploration goes? And, you know, is that a thing that has to be looked at, I guess?
Those are good questions. So, for some of you who don't know, Europa Clipper is a mission that's being sent by NASA to visit and orbit around Europa to find out more information about, I guess, the geochemistry of the environment from the surface. The European Space Agency also has a mission that's going known as JUICE. They will launch about a year apart, maybe, or within a year. For me personally, one of the more interesting things I want to find out from these missions is a bit more about the chemistry of like the salts and the environment, and if they can sample any plume material that may occur whilst it's there. That will be really helpful because that will feed into my research. So perhaps what I didn't mention was my research is very much focused on trying to identify what that subsurface ocean looks at. So any information that we can get about the geochemistry can help constrain all the models that I've done. Because at the moment I just look at a broad range of like potential candidate compositions. But what I want to do is narrow it down. So any type of information from that would be great. But I do have to wait a few years to get it, which is kind of frustrating. What was the other question, sorry, about people's perception of how long it takes?
Yeah, just that, you know, it's like, oh, it's been like 2 decades of like, oh yeah, no, Europa, there's probably a sea under there, there could be life there. And it's like, that was like 2 decades ago. I mean, I guess from a personal experience, I'm like, why does it take so long to be like, oh yeah, there's probably an ocean under there, there could be life under there, and then it's like 2 decades later, it's like, oh, we're going to probably send a satellite now, it'll take about 6 years to get there, and then maybe after that, we might consider the possibility of going and look, and it's just like, it seems to take a long time.
Yeah, okay. So in terms of sort of like, in terms of the information that we get back quite a lot of information from these different missions, but we still need to like add context to them, and be able to interpret the information that we're getting and what we're seeing, and that can sometimes take additional experiments once that data comes back. So it does take a bit of time to be able to fully interpret the information. I think you can still see that from like the Mars missions, where like whilst the rovers like still going on after like decades, we're still like trying to better interpret the data that we're getting back. And missions to different bodies in the solar system are really expensive. And there's only a finite amount of money that the space agencies have to go and explore them. And they kind of do have to sort of ask the scientific community about where, sort of like priority targets, I guess, and then that can inform the decisions that they make. And all these things kind of take time. And of course, it just takes time to get to these places as well. Like Mars is what, like 6 months?
6 months or 2 years, depending which way around the sun you go, basically.
Yeah, and then like the icy moons are about 7 years. So it's just unfortunate due to our propulsions.
You'd have to choose your PhD topic carefully, otherwise you're... Yes.
I'd just add to that about the time thing. So currently these Europa Clipper and JUICE missions are going to be getting there in the early 2030s. They were designed and initiated based on the results from Galileo and back that was in there in 1996. They are already planning the next set of icy moon missions, but they are currently being worked on by proposal teams who will all be retired or dead by the time they get there. In fact, they've specifically wanted to have like very early career researchers, because the early people who are just out of their PhD now, while those missions are being initially planned, will be professors, and in the 2050s, when the results from those missions will get back, because space is really hard, and we hear about the things we do find, but the unknown questions are so many more. Yeah.
Kids, we need you.
if I can add, it's also an engineering problem. It's not so much just science, because wanting to go there is one thing, but adding the feasibility of, is it actually really possible, is especially hard for some planets like Venus, for example. So it takes a lot more preparation time. And also for icy moons, anything going into the outer solar system is also very difficult.
Yeah, you can't use the latest technology in space, because it will basically break. If you're going to spend €1 billion on sending a mission, you need to be very confident that the camera is going to work. So you have to use hardware that's really well understood. And places like the orbit of Jupiter are really, really bad for technology, which is something else that the OU does as it happens. But anyway.
So things are very over-engineered.
And they still break.
Is that why some of these rovers, when they're designed to last 2 years, but then they last for a long time?
So industry will be given, say, you need to be able to guarantee that this piece of equipment can operate in a plus or minus 200 degree thermal window on a different planet for at least 90 days. And if you can be confident and that you can demonstrate that it will do that, it probably will last longer. For example, the MER rover, which lasted 14 years. So, yeah.
Thank you. There was a question back up there, and then we'll come down to the front. So could we go to, yes. Oh, I don't know how you can get there. Can you, it's just here behind the camera. It's just here behind. So if you go through the middle row. Yes, just here.
There's a lot of excitement about the possibility of life on other planets, and we keep finding distant planets which seem to have all the right ingredients, right distance out and that. I remember coming across people who became enamoured with the idea of probability, and that it doesn't matter how outlandish something is, if give it enough time and resources, it'll happen. Now, numbers tend to do a different game on that, and they play their own game. So, you can take a dice and throw a million sixes, but you probably won't. It'll probably keep working out. So just to draw those elements together, we're looking for those planets and saying, yeah, that's the right place, that's the Goldilocks planet. But is it not more about how likely or unlikely is it for those ingredients to produce life? We got a 1 in 3 hit rate here in our own solar system, which is brilliant. But how often do we think that planets are going to go the way of Earth, and how often are they actually going to go the way of Venus or Mars?
Okay, question of probabilities. While that's happening, we might move the microphone down. You had a question?
I do.
So we'll answer this one, and the microphone will come to you. Probability of life. Just a small question.
Very
You got all the
existential.
rocky people here.
Yeah.
So.
Yeah.
I'm not sure about that one. But I do know, like, even on Earth, we do find life in very extreme environments, like places that we never thought that they could survive. And that changes our perception of where life can exist. So, I don't know, does that increase the probability? I don't know.
I think it depends on what scale you're looking at things. If you're talking about the like all the potential planets across the, all the potential time in all the different galaxies across the universe, then it's quite likely that something else will be similar to what we've had. But on the other side of that, the history that Earth has that brings us to here today to this auditorium is also incredibly unlikely. And there's many, many events which in our history, geological history, which seem kind of improbable. And if they hadn't happened, perhaps we wouldn't have, have been here today. For example, like the dinosaurs were wiped out by a meteorite. If that meteorite and other things, other factors, if that hadn't happened, would mammals have evolved in the way in which they had now? But then a different meteorite could have struck Earth at an earlier time, and could mammals have evolved 100 million years earlier in history? So it's a sort of a mixture of, there's so many things that anything is probably possible somewhere, and also everything we have is incredibly improbable that it's actually come to be where it is, which is quite exciting, really.
Yeah. I mean, there's also the factor that we don't actually know. Whilst we know some things about how life evolved on Earth, there's still like loads of questions that still exist around it. And at the moment, how life existed on Earth was potentially in a different environment to what is supporting the life we see today. And of course, a lot of what we're looking for out there is based on what we see today. So actually, we probably need to understand how life evolved a bit more on Earth before we can really fully understand exactly how probable life is anywhere else in the solar system or universe, I guess. I think.
Last comment, yes.
I also think that sometimes you have to take a diametrically opposite approach, which is you don't set out to just solve the question whether there is life elsewhere. What I think we also need to do is to continuously use our creativity and imagination and actually try to first understand the natural world around us. Because if you do that, then there would be many, many processes. As Peter said, there are still so many unknowns, so many things we don't know. You never know. Without actually looking for something, you end up discovering that because you have tried to understand the processes behind that. And when you put all of that together, the ultimate output is, maybe in this case, it's life, or it could be something else. So I think it's both approaches are being followed and being done. So here, whoever is listening, and I would just like to ask you to keep your mind open to all possibilities and just be curious and ask questions about everything and then try to find an answer to that. That's all we can do as humans.
Thank you. We'll come to your question, and then I'll come to you.
Mine's a very quick question.
Great.
And maybe a silly one, I don't know.
No, not at all.
So, which planet does Earth resemble in composition, in whichever way now? And with the subject of global warming that we're all really aware of, which planet is it heading to look more like?
Looks like it's one for you, Julia.
Yes, so compositionally, it is very similar to Venus. And also from the size. There are slight differences, probably in the interior. Unfortunately, we don't know as much about the interior of Venus as we would like to. So we would prefer future missions, but we already talked about the difficulties of these. Overall, I think the scenario for Earth, if the climate actually moves in that direction, could be a runaway greenhouse effect, and then it could look very similar to Venus. And this is also why we are very interested, or many people who study the climate are very interested in how the extreme climate developed on Venus. And for Venus, it is because Venus is closer to the sun, so it obviously got more of that heat. But for Earth, it is depending on I mean, there are also theories once the sun actually gets to a state where it's it's running out of energy, it will just kind of burn everything. And so if Earth doesn't have that path until then, it definitely will get burned until at that point.
So when you referred to priorities, in terms of where research funding is directed, should that not have a priority? When we focus on our own planet, which you said first, should it not have some priority, or does it have some priority?
So just because we don't have the microphone, I'll repeat the question. So the question was, because we're facing climate change challenges, should looking for something that's similar to what Earth will be like in the future be driving the priorities of planetary research?
I was going to say two things. Firstly, I think there is a huge priority, and if you look at the amount of sort of research funding that goes towards sort of planetary stuff, it's actually very small compared to the amount that goes to all the other kind of understandings. It's the exciting cherry on the massive understanding cake, really. But also, looking at other planets allows us to reflectively think about how our planet can change and the consequences of those changes. So by studying, say, Venus or Mars, we can use them as like a natural laboratory for what happens if the initial conditions were different. In the case of Mars, it's small and got much less energy, or Venus, where it's surprisingly, in fact, alarmingly similar, and yet is in a very, very different state to how we are today. Yeah.
Great, thank you. So we have someone in the blue shirt, and then we'll come to the person in the purple shirt.
A few of you have mentioned that you're using models. There's a famous but telling phrase that all models are wrong, but some are useful. So how do you think you can verify that your models are useful, especially given probably the most famous thing happened when space exploration is that we didn't expect that?
Nice question. Who's going to take it on?
Models.
Yes, I mean, ideally we would not have to use models because we actually had indefinite amounts of money to study everything that we would like to. But that is not the case, and that is not even the case for Earth. There are many areas on Earth that we just cannot reach. We cannot reach the deep crust or the mantle. There are areas we just don't know anything about. So the next best thing is either experiments or models, and models are nothing else but an experimental setup on a computer, more or less. That's usually what I tell people. And if we do an experiment, particularly in earth sciences, in geology, any experiment that we do has to limit the conditions. So we have huge processes going on Earth. We have plate tectonics. We have rocks being moved over timescales, over large areas. We cannot understand that just by looking at it because we're not getting that old. So to understand this, we need both experiments and also models, because otherwise we will just not get around to understanding these processes. So yes, we always have to make sure that we model in a way that we point out where our limits are. But I think, especially in space science, a lot of things just rely on models, because otherwise we just cannot do the science that we really need, and also fundamental groundwork that we need for missions. So it is a bit of a it is tricky. I don't think that science without modeling is going to work, because then we would be very, very limited to. We do reality checks. We do use whatever we have, and for Venus that is very little. So we do use what we have, and then we just have to. I think one of the things that we can do is that we use a parameter space. So we use the amount of possibilities that are reasonable, and then once we have more data, once we get a mission that actually gives us more data, we can then narrow down the possibilities because the model already considered them. So let's say we assume that the atmosphere, we have a parameter space for the atmosphere, and then we actually send a mission to Venus that measures the atmosphere much better than what the analysis we have, we can then say, okay, but this is the point, and this is what the model actually suggests how it formed. So this is usually what we do.
Did you want to add to that?
Yeah, it's just amazing. It was a great description of what models can do, but everything gets upended every often. I don't know how many of you actually had a chance to handle some meteorites downstairs. I mean, that's why space is so fascinating. Every so often, we get these rocks from space. Either they come on their own volition through meteorites, or we go and collect them. And then you collect the real data. That then forces the models to be adapted, and that's what goes into actually validating those models. And if they don't get validated, the new sample, new material tells you that, okay, you need to change your model. We do that. So I think there is a concerted effort that is going on where experiments are done, natural samples are measured, models are developed, and it all goes into cycles. And it's just, that's what we do on a daily basis.
That iterative development is little step by little step
That's
eventually makes a big step. Great, we'll go to the man in the purple shirt, but I can see there's lots of young people in the audience and I'd really love to hear from you. So if you've got a question after this one, please put up your hand.
Yeah, firstly, congratulations for being trusted by the Chinese. That's quite an amazing achievement. It's I presume the Chinese actually went with a probe to get these rocks. And my question really is about why haven't we seen somebody on the moon for a long, long time? And the question is in and around the Van Allen belt. As you know, it's a huge radiation problem for us. And last time I saw somebody being interviewed, which was in America, he was a NASA scientist, astronaut, and he said that we have lost the data on how we got through the Van Allen belt, which I just find very interesting. But you said that part of what you're doing is to try to see if we got resources that when we go out into space, so we got water, we've got oxygen, and part of your work is to try and achieve, to see if we can actually do that. How are we going to get through the Van Allen belt to get there? Because it's such a high radiation, we are just fried every time we get anywhere near it. And it's interesting, the Chinese have not actually gone to the moon with a man, I feel.
That's definitely yours, Mahesh.
Okay. Yeah, well, thank you very much for the compliment. I think that's one thing that we do have in the UK is that we have a huge reputation for the research, the scientific research that we do, and particularly in Milton Keynes at the Open University. So I cannot tell you that, what a privilege it is to be selected to receive those samples, the only person in the country. So that's aside, China is developing a program of crewed missions. And soon you will see, I can tell you, you will see not only Chinese taikonauts walking on the moon, but there would be other astronauts from other countries walking. I can't possibly comment on the knowledge loss that you refer to, but I think what that person is trying to say is that, as Peter was saying earlier and others have alluded to, space is hard, it takes time, it takes decades. You lose that knowledge base from time to time. You do have people retiring and sometimes no longer with us. So, but I can assure you that that knowledge still exists, and there will be people walking on the moon. And just spare a thought, while we are discussing about reaching to Jupiter and the icy moons and all of that, that takes 5-10 years to get there. It takes less than 3 days to get to the moon. And you just said, how many have you seen actually recently? 0. How many successful missions have landed on the moon recently? You can count on your fingers, 2 or 3, but majority of them have failed. So space is hard, not easy. But surviving through Van Allen belt is a real issue. The Apollo astronauts survived. In 2 years' time, hopefully you will see the Artemis mission taking the next adventures on a round trip to the moon. They will not land on the surface of the moon, but they will have to go through the Van Allen belt to get to the moon and come back. Those astronauts have been selected, you know that. And when I was in China, I learned that the human space program in China is also planning to land taikonauts before 2030.
I suspect actually in China you'll find, I don't know if that's on, so you'll probably find in China they'll use artificial intelligence robots. I work in AI myself. And you'll probably find, I'm predicting this, that humans, you won't see them, but we will download our consciousness into these robots and they will go. There's a quick follow-up question here.
You know more than I do, but when I was there in Shanghai, they had the first marathon for robots the same week. Yeah.
Sorry, I'm being told that I need to wrap things up. So I was just going to offer someone else a question because you've asked one, but hopefully you can ask your question afterward. Do we have one more question? Yes, we've got one here. Excellent. Thank you for that's very kind of you.
What else is in your moon rocks?
What else? What else in my moon rock? Well, in some ways, moon rock is no different than an earth rock that you find. And that's the beauty of it. And that's the beauty of the moon is actually it is almost identical to the earth. And we talk about other planets and things that we haven't been there, we haven't explored it that much, but moon we have explored a lot. And in a lot of respects, it's made up of the same materials, same elements. And that's why it's so much easier to devise techniques and technology to make use of the lunar material that is there in the same way that you do here on Earth when you are going for mining. You are interested in copper, let's say, for example, or iron or something. You might find that actually same type of rock types are available, sometimes not in that quantity, but the bottom line is that in moon rocks you have almost everything that you find here on Earth. Everything is useful, every single bit of it, because on Earth you get everything that you're right now, you're talking through the mic, that has got certain rare earth element that has been extracted from rocks here on Earth. You will have the same thing that you do on the moon.
Thank you very much. So we've run out of time for more questions, but this was only the first in a number of events from the Open University in partnership with the International Festival Milton Keynes. So weather permitting, Luke's sculpture will stay where it is for the next 2 days. And tomorrow at 2 p.m, he's going to be here speaking about how he creates sculptures of viruses, the moon, and diatoms with such astonishing accuracy. Also here tomorrow in the evening, Professor Susanna Swenza will be talking about how the NASA Curiosity rover has been exploring the Gale crater on Mars since 2012 and her role in what that's uncovered. So I encourage you to come back tomorrow to hear both of those things. On Sunday, we have Dr. Elliot Sefton-Nash from the European Space Agency sharing a story about how Mars has evolved and how it may have harboured niches favourable to the emergence of life, which follows on from what we've been talking about this evening. And beyond that, academics from the Open University are leading workshops on writing, creative, interactive harmonies and songwriting. Other researchers are creating a community project on why it's great to live in Milton Keynes and how it can be even better. And also hosting a Climate Change World Cafe. So please go to the International Festival Milton Keynes website and search for the Open University to find more details about those and book if you need to. So that just leaves me to thank again our speakers. Thank you, Mahesh, Yulia, Peter, and Nisha. Thank you to everyone behind the scenes who's made this possible, all of the organising, all of the audiovisual folks as well. These things don't happen easily. And lastly, thank you very much for coming. Thank you for your questions. It's the bit that made, no offence, this particularly interesting. I hope you enjoyed the evening. My name's Julia Cooke. Good night.